Hi, my name is Jonathan Mousley. I'm a mathematics PhD student at Duke University. Today I'm going to be talking about the row echelon form of a matrix and how that relates to bases for the row space and the column space. I'll start by talking about a little bit of a review relating to the row echelon form of a matrix. If you're not familiar with what the row echelon form of a matrix is, this won't really be the best video for you to watch now. You're encouraged to go learn that concept first. After I finish that review, I'll be talking about how you can use the row echelon form of a matrix to find a basis for the column space. And then next, I'll be talking about how you can use row echelon form to find a basis for the row space. Finally, at the close of today's video, I'll give an example of doing all of this with a particular matrix A. So first of all, I'm going to fix a matrix A to be M by N. And then I'm going to define Ci of A to be the column index of the first non-zero entry of A in row I. If row I of A is a zero row, I'm going to define Ci of A to be infinity. Then I'm going to say that A, this matrix, is in row echelon form if Ci of A is greater than or equal to Ci minus 1 of A for 2 less than or equal to I less than or equal to M. And then once I have that definition fixed for row echelon form, I can define the pivot of a matrix in row echelon form to be the first non-zero entry in each row of A. So remember, the heuristic here of what it means for a matrix to be in row echelon form is it has pivots, and the only entries below these pivots are zero entries. So looking at some examples, I have three matrices A, B, and C. A is in row echelon form, B is not in row echelon form, and C is in row echelon form. I have the pivots for the matrices that are in row echelon form circled in red. And then B, this matrix that's not in row echelon form, the reason for that is the 3-1 and the 3-2 entries are both not zero entries. So that violates this condition for all of the entries below pivots to be zero for this matrix B. All right, so let's talk a little bit about finding the row echelon form of a given matrix. So the idea here is when I give you a matrix, we can perform row operations on A to arrive at the row echelon form. And I want to give you a little bit of a graphic and an explanation for this particular case of when I have a 3x3 matrix. So remember, the philosophy here is I start by identifying a pivot row, and then I'm just going to perform eliminations to get all of the entries below my pivot entry to be zero. So here, my pivot row is row 1, and this entry marked in red is going to be the entry that I work to eliminate. So I'll do that by taking a multiple of this pivot row and adding it, in this case, to row 2. And then these entries that are marked purple, that's just to signify that those entries have now changed. So they're not necessarily the entries that we started with. And then next, I've eliminated that 2-1 entry. Now I want to eliminate the 3-1 entry. So I'll go ahead and do that again with some kind of multiple of row 1 being added to row 3. The result there is then a matrix that looks something like this. Again, that purple is signifying that those entries have been updated. So now I actually have zero entries below my pivot. Now I want to move on to my next pivot. So now I'm going to actually add multiples of row 2 to the things that I need to eliminate. That entry marked in red is the thing that I want to eliminate. And so I'm going to take appropriate scaling of row 2 and I'm going to add it to row 3 to eliminate that red thing. Okay, and then again, I'm kind of showing a change in color here for this 3-3 entry to just emphasize that it wasn't the entry necessarily before I did this operation. After we complete this process, we have this as our result. As you'll see here, we're looking at something that has zeros below all of our pivots. One thing I want to make a comment of, though, is this example I've run through is really just the case where we have a 3x3 matrix and no row swaps were necessary. So I'm intending to just kind of refresh your memory on this. Keep in mind, there is a possibility, even in the 3x3 case, where you might run into issues with your pivots, maybe hitting zero entries where row swaps would be necessary. I want to emphasize that we can encode these row operations I was just talking about to be invertible matrices E that perform this operation on A when we actually do the multiplication E times A. So as an example, again, looking at 3x3s for simplicity, Say I want to add 3 of row 1 to row 2, well, I can actually encode that information in a matrix that's here on the right side of the screen, where it's an identity matrix, but I just update that 2-1 entry to be 3. That 2-1 entry is going to correspond to what multiple of row 1 I'm adding to row 2. And in this second example, we're adding -2 of row 2 to row 3. We can again encode that as an elimination matrix, where we start with an identity matrix, but replace the 3-2 entry to be -2 to again represent that we're subtracting -2 of row 2 from row 3. All right, so now I want to talk about the row echelon form of A and bases for the column space of A and how they relate. So the first thing I'd like to point out is that A and the row echelon form of A satisfy a relation that's written here. That relation is saying that I can get the row echelon form of A by multiplying A by a sequence of elimination matrices that perform these row operations. The important thing, though, is that each elimination matrix here is invertible. Because each is invertible, I can actually say that this entire product, En times En minus 1, all the way down to E2 times E1, is itself invertible. So that means that I could multiply that relationship up above by the inverse of this product on both sides, and then I would actually get out that A is equal to some matrix times the row echelon form of A. All right, so now I want to leverage this equation here in green to say something about how the row echelon form of A and bases for the column space of A relate to one another. Really what I want to emphasize to you is that linear dependence in the row echelon form of A implies linear dependence in A itself. So say I wrote the row echelon form of A as being this matrix here. I'm just labeling the columns of the row echelon form of A as V1 through Vn. And so I want you to imagine that these columns here have some kind of equation of linear dependence. So C1 V1 plus all the way up to Cn Vn is equal to 0 for some Cj not being equal to 0. So in other words, there's some scalar in this equation that isn't 0. So what that would be saying is that the row echelon form of A times this vector C1, C2, all the way down to Cn is equal to 0. Now I want to direct your attention to what we had before, which was that A is equal to a matrix times the row echelon form of A. So if I take a look at A and I multiply it by that same vector above, C1 through Cn, I'm going to get out this. So I'll have this matrix, the inverse of En times En minus 1 all the way down to E1 times the row echelon form of A times this vector C1 through Cn. But remember, this vector C1 through Cn is in the null space of the row echelon form of A. So that multiplication there, the row echelon form of A times this vector of C's is equal to 0. So ultimately, what we're getting for this vector A times C1 all the way down to Cn is just the 0 vector. So the columns of A are linearly dependent with the same scalars Ci. All right, so we've talked a little bit about the relationship between the row echelon form of a matrix and its column space. Now I want to do the same, but more about the row space and its relationship to row echelon form. So to find a basis for the row space of a matrix, we're in search of a linearly independent spanning set of the row space of A. And I want you to remember that the rows of A, by definition, are going to be spanning for this space, but they just might not be independent. So the big idea with all of this is I'm going to show you how the rows of the row echelon form of A are still spanning for the row space of A and are independent. The central idea to all of this is that elimination matrices and row swaps preserve the row space. Let's take a look at this with elimination matrices. Say E adds C of row I to row J. Then we have something like this, where the rows are originally R1 through Rm, and then they become R1 through Rm, except for in row J, where it's now row J plus C of row I. So the row space of A is then the span of the original rows, and the row space of the result, E times A, is the span of the original rows, except again that change in the jth row, which is now Rj plus Cri. I want you to notice that the row space of EI is actually going to be a subspace of the row space of A, because the rows of EA are just linear combinations of the rows of A. Also notice that the row space of A is a subspace of the row space of E times A. This is true because all of the rows of A are actually themselves inside the row space of E times A. The rows that aren't the jth row are definitely in there because they are part of the spanning set that defines the row space of E times A. Rj is also a vector inside the row space of E times A because it's a linear combination of the vectors inside the spanning set that defines the row space of E times A. I have this particular linear combination written here, and notice those blue vectors are just the rows of the matrix E times A that make up the spanning set for the row space of E times A. So because these subspaces fit inside of each other, they actually have to be the same subspace. So the row space of A is equal to the row space of E times A. Now let's take a look at how row swaps preserve the row space. But this is definitely going to be true because we have the same rows after we perform a row swap. They're just in a different order. Now remember, we get the row echelon form of A from A via multiplication by E's and row swaps. So because row swaps and multiplication by elimination matrices E preserve the row space, that means that the row space of the row echelon form of A is equal to the row space of A. And even better, linearly independent rows of the row echelon form of A are a basis for these spaces. I'd like to close this video with an example that shows how all of this ties together. So I've presented a matrix A here, and I want to find the bases for the column space and the row space of the matrix. I'm going to use the row echelon form to accomplish this. So pause the video now and see if you can find the same row echelon form that I did. This is the row echelon form for the matrix A. Taking a look at this, I see that the first two columns of the row echelon form are linearly independent, specifically the columns 1, 0, 0 and 0, 1, 0, 0. And the third column is a linear combination of these two. Column 1 plus 2 of column 2 gives me column 3. And by our first recollection, this is exactly the same situation for the matrix A. Column 1 plus 2 column 2 gives me column 3. So because column dependencies of the row echelon form of A are column dependencies for A, we can conclude that the first two columns of the matrix A are a basis for the column space of A. Moving on to recollection 2, looking at the row echelon form of A's rows, we see that the first two rows are linearly independent because they aren't scalar multiples of one another. So I can conclude that those rows form a basis for the row space of A. Again, in summary, I have that the first two columns of the matrix A form a basis for the column space of A, and the first two rows of the row echelon form of A form a basis for the row space of A. That completes the content for today's video. Thanks for watching, and I'll see you next time.